We now discuss the solution of problems from group theory that have appeared in the TS set 2019 and 2023 examinations and Junior Lecturer 2004 and Degree Lecturer 2007 examinations. And the problems are related to Sylow's theorems. And all these questions are relevant to JL, the aspirants of JL, DL, TS set, AP set examinations also. Now let us get familiarized what are Sylow's theorems. To get into the Sylow's theorems, we first know the concept of a Sylow p subgroup. Before that, we talk about a p group. The first one is, let G be a group and P be a prime number. A group of order p to the power of alpha for some alpha greater than or equal to 1. If the order is the power of a prime, where the power is greater than or equal to 1, is called a p group. Suppose you have a group of order 32. Then it will be, the order is 2 to the power of 5 and it is called a 2 group because p is equal to 2 a prime. Now, the subgroups of G, whose order is p to the power of alpha, are p groups. So, if you take a subgroup of the above group, it will be a p group and they are called p subgroups. Now, the concept of Sylow p subgroup comes now. If G is a group of order p to the power of alpha multiplied by m, where p is a prime, p does not divide m, then a subgroup of order p to the power of alpha is called a Sylow p subgroup of G. So the order of G is p to the power of alpha into m, where p is a prime and p does not divide m. It amounts to say that p to the power of alpha divides order of G and p to the power of alpha plus 1 does not divide order of G. Then the subgroup of order p to the power of alpha is called a Sylow p subgroup of G. The number of Sylow p subgroups of G is denoted by NP. That means we can count the number of Sylow p subgroups of G, and that is denoted by NP, and it is given by the formula in the third Sylow's theorem. So now we go to Sylow's theorems. So first we have G is a group of order p to the power of alpha into m, where p is a prime and p does not divide m. Agreed. Then the first Sylow's theorem says G has a Sylow p subgroup. So the first theorem, Sylow's first theorem says G has a Sylow p subgroup. It is guaranteed. It is guaranteed. 2. Any two Sylow p subgroups of G are conjugate in G. So if you have more than one Sylow p subgroup of G, then they are conjugate. The number of Sylow p subgroups of G is of the form 1 plus Kp, that is, the number of Sylow p subgroups of G are denoted by NP, n suffix p. So that means NP is congruent to 1 mod p. 1 plus Kp means when you divide by p, the remainder is 1. So it is of the form 1 plus kp, and np is congruent to 1 mod p. Further, np divides this m, which is free from p, So that part of order of G which is free from p is m. So np divides m. So this is you have to remember. Agreed. The third Sylow's theorem is very, very important because we are going to count the number of Sylow p subgroups of the given group. Agreed. Now, suppose the group G has only one Sylow p subgroup of G. Then what can you say about that subgroup? And that subgroup is normal in G. So that's the theorem, and this is a necessary and sufficient condition. A Sylow p subgroup of a finite group G is a normal subgroup of G if and only if it is the only Sylow p subgroup of G. That means, so if you have H is a Sylow p subgroup of a finite group G, and NP is equal to 1, NP, the number of NP is equal to 1, then H is normal in G. NP is 1, it amounts to say that the only subgroup, the only Sylow p subgroup of G, that is H is the only Sylow p subgroup of G, then H will be normal. Agree? So that's so H is normal in G if and only if NP is equal to 1. Now, the definition of the simple group. A group G is said to be simple if it has no non-trivial normal subgroups. That is same as if its only normal subgroups are the identity subgroup and the group itself. And these are the only two normal subgroups of the group G. Then G is said to be simple. This definition is required for us. Agreed. Now, having known those results, we attempt now a question that has come in TS Set 2019 examination. What is the question? Question number 70, and with this ID. The question says, let G be a simple group of order 132. The number of subgroups of order 11 is, how many subgroups of order 11 are there? So we are given 4 options. Options are here. Now how do we attack this question? So first of all, we have the order of G is 132. Write its prime factorization. So 11 into 12. 11 into 12 can be written as 2 square into 3 also you can write. But we want only the number subgroups of order 11. That means the Sylow 11 subgroups we want to talk about. So 11 into 12 we have written. No problem. No problem. Now 11 divides order of G. And 11 square does not divide order of G. So by first theorem of Sylow, G has a Sylow 11 subgroup, or G has Sylow 11 subgroups. How many? That's the question. That's the question. So now N11. What is N11? The NP. NP is the number of Sylow p subgroups. So N11 is the number of Sylow 11 subgroups of G. And by the third theorem of Sylow, it is of the form 1 plus kp. That is, NP is congruent to 1 mod 11. And N, that means, and there is another condition, that is N11 divides 12, which is free from 11. Which is free from 11. 11 is not a factor for 12. So N11 divides 12. So N11 is congruent to 1 mod 11 means N11 can be 1, add 11, 12, add 11, 23, etc. etc. And N11 divides 12 So n11 divides 12 and n11 should be in the above also. So the common is n11 is equal to 1 comma 12 because the commonality we take. n11 divides 12, 1 divides 12, 2 divides 12, 3 divides 12, 4 divides 12, 6 divides 12, 12 divides 12, all that you can consider. But you know, the above one common to that and this, both the conditions, this and this, both the conditions. Therefore, n11 is equal to 1 comma 12. Suppose you say n11 is 1. Then G has only one Sylow 11 subgroup, say H. If you have only one Sylow 11 subgroup, then it is normal in H. So that means H is normal in G. So when H is normal in G, so H is a non-trivial normal subgroup of G. So G is not simple. But G is given to be simple here in the question. Therefore, it's a contradiction. Therefore, n11 is not 1. So n11 must be 12. So the number of subgroups of order 11 is 12. The answer is option 3. So the answer to this question is option 4, not 3, option 4. So wherein you got the answer is 12. So the number of subgroups of order 11 is 12. So that's the question that has come in the TS Set 2019 exam related to Sylow's theorems. Let's move to the next example. So this is TS Set 2023 examination. It has come. Question number is 70 and with this question ID. And what is the question? Let G be a simple group of order 216. Then the number of subgroups of order 27 can be. So 4 options are given. And this is same as that 2019, the question that has appeared in the 2019 examination. So now solution is very on the similar lines. You write given G is a simple group of order G, simple group, and order of G is 216, and write the prime factorization 2 cube into 3 cube, and note that 3 cube because the subgroups of order 27 is there in the question. So we have to talk about 27. 27 means 3 cube. So note that 3 cube divides 216 and 3 to the power of 3 plus 1 does not divide 216. Therefore, by the first Sylow's theorem, G has a Sylow 3 subgroup, say H, of order 27. Let N3 be the number of Sylow 3 subgroups of G, and by the third Sylow's theorem, N3 is congruent to 1 mod 3, and N3 divides 2 cube, so which is free from 3. So 2 cube, that is 8. So that is N3 is equal to 1 plus 3k. N3 is congruent to 1 mod 3 means 1 plus 3k, and that may be 1, 4, 7, etc. N3 divides 8. N3 divides 8. And both these things, both of them must be satisfied. Then N3 is equal to 1 comma 4. So if you say N3 is 1, then it is the only one normal subgroup, only one Sylow 3 subgroup. If it is only one 3 Sylow subgroup, then it is normal. So then H is normal in G, but G is given to be simple, and H is a non-trivial normal subgroup of G. So therefore G is not simple, but it is given to be simple. Therefore it is a contradiction. Therefore it cannot be 1. So when it cannot be 1, then N3 must be equal to 4. That is, G has 4 Sylow 3 subgroups of order 27. So, so, so the number of subgroups of order 27 is 4. So the answer is option 4. So that is the question that has come in TS set 2023, which is very similar to the earlier question. Agreed. Now let's get into another question. This question has appeared in the junior lecturer's examination held in 2004. Question number is 36. The number of normal subgroups of order 7 in a group of order 14 is. We are given options, 4 options here. Now we take, let G be the group of order 14. The order of G is equal to the prime factorization. 14 is equal to 2 into 7. So now 7 divides order of G. 7 squared does not divide order of G. So by Sylow's first theorem, G has a Sylow 7 subgroup of order 7. Agreed. How many? So let us say N7, the number of Sylow 7 subgroups is given by N7 is congruent to 1 mod 7 and N7 divides 2, free from 7. So 7 is not a factor. That part you have to take. N7 divides 2. So N7 divides 2 by Sylow's third theorem, and N7 divides 2 will give you only 2 options. N7 is equal to 1 or 2. Why? So N7 is congruent to 1 mod 7. So this will give you 1, 8, 15, etc. So N7 is congruent to 1 mod 7 will give you 1, 8, 15, etc. N7 divides 2 will give you 1, 2. What is the commonality? N7 is equal to 11. So N7 is 1, not 11. N7 is equal to 1. So N7 is congruent to 1 mod 7. You take the values 1, 8, 15, etc. N7 divides 2 is 1, 2, only 2, and take the common. So then N7 will be equal to only 1. So there is only one Sylow 7 subgroup of order 7, and if you have only one Sylow 7 subgroup of order 7, then it should be normal in G. So it should be normal in G. So therefore there is only one normal subgroup of order 7 in G. Agreed? So we have considered all Sylow 7 subgroups of order 7, and fortunately or unfortunately it is only one, and that is normal, and thereby we got all the number of all the normal subgroups of order 7. So that is only one. So there is only one. So the answer is option 2. That is only one is the answer. So that's the question that has come in JL 2004 examination, and I think I have an alternate solution for this. That is alter. Alter means alternate solution. So let's see. So that's the question, and those are the options are not given. Options. So solution. Let G be a group of order 14. Write the prime factorization 2 into 7, and now recall Cauchy's theorem. The Cauchy's theorem says let G be a finite group and P is a prime number that divides the order of G. Then G has an element of order P. So here 7 is prime number, 7 divides order of G. Therefore G has an element of order 7. So now 7 divides order of G, 7 is a prime, and therefore by Cauchy's theorem G has an element A of order 7 by Cauchy's theorem. So let us say, let's now consider H is equal to the cyclic group generated by A. Then order of H is 7. Then the index of H in G will be given by order of G by order of H. And that's the formula when order of G is finite and order of G is 14, order of H is 7, that is equal to 2. And any subgroup of index 2 is normal. So H is normal in G. So thus G has a normal subgroup of order 7. We wanted to, that normal subgroup is H. We wanted to show that this is the only subgroup, and thereby the number of normal subgroup of order 7 will be 1. So now assume, so to prove that it is the only one, so we assume the contrary, that means assume that you have two distinct normal subgroups of order 7 of G, let us say H and K. Besides H, there is also a K, let us say, what you are thinking. Then what will be H intersection K? H is a group, K is a group, subgroup. H intersection K is also a subgroup, and the order of H intersection K. And what is H intersection K? H intersection K is a subgroup of H and a subgroup of K. So by Lagrange's theorem, order of H intersection K must divide order of H and order of K. That means order of H intersection K must divide 7. That means order of H intersection K can be 1 or 7. If order of H intersection K is 7, H is equal to K. Therefore, order of H intersection K is 1. Therefore, H intersection K is identity element alone. And now recall this result, very famous result. The order of HK is equal to order of H into order of K by order of H intersection K, and that will be equal to order of H is 7 into 7 by 1, because order of H intersection K consists of just one element, and that is 49, which is greater than 14. That means the HK, the product HK will have 49 elements, and all those elements must be elements of G, but unfortunately G is of order 14 only. Therefore, it is not possible. So this is a contradiction. So this contradiction shows that your assumption that there is more than one normal subgroup of 7 is not true. Therefore, we have only one normal subgroup of order 7. So G has only one normal subgroup order 7, and that is our answer, option 2. So that is the discussion about the question, the alternate proof, alternate solution for that question that has appeared in JL 2004. Lastly, we also see one more question. Of course, this is not having any bearing on Sylow's theorems. And this question has come in degree lecturer's examination held in 2007. The example is question number 62. If G is a group of order 36 and H is a subgroup of G of order 9, so H is a subgroup and order of H is 9, then the order of a normal subgroup N not equal to identity element alone of G in H is. So the how many normal subgroups, non-trivial normal subgroups N of G are there in H. That is the stress. So we are given options 2R3, 3R6, 3R8, 3R9. So solution, given G is a group, H is a subgroup of G, given order of G is 36, given order of H is 9. Agreed. Now, the index of H in G, because G is finite, so order of G by order of H, that is 36 by 9, that's equal to 4. So this will be 36 does not divide order of G. That means the order of G does not divide the index of H in G factorial. Here we recall a lemma. If G is a finite group, then H is a proper subgroup of G such that the order of G does not divide the index of H factorial. So then H must contain a non-trivial normal subgroup of G. And in particular, G cannot be simple. This is the result. You can see this result in Topics in Algebra by Einstein at page number 73. You can also see this result and as index theorem in Contemporary Abstract Algebra by Joseph A. Gallian, page 426. Let's call this as the index theorem. So what is that you have? G is a finite group. Yes, G is a finite group. And H is a proper subgroup of G. Yes, order of H is 9, order of G is 36. Therefore, H is a proper subgroup of G. And the order of G does not divide the index of H in G factorial. Correct. Then what it says? H must contain a non-trivial normal subgroup of G. So, by index theorem, H contains a normal subgroup N not equal to the identity element alone because non-trivial of G. H contains. This means that is N is a normal subgroup in G and N is contained in H. H contains N, but N is normal subgroup and non-trivial. So N is contained in H. So what do you mean by N is contained in H? N is a normal subgroup and H is a subgroup. So N is a subgroup of H. N is contained in H will imply N is a subgroup of H. So by order of N divides order of H by Lagrange's theorem. Agrees? N is a subgroup of H. The order of N must divide order of H. Order of H is 9. So order of N divides 9 means order of N is 1 or 3 or 9. But we have written order of N is 3 or 9 because N is non-trivial. N is not equal to the identity element. This means order of N is not 1. Order of N. So because of that 1 is removed. So what the theorem says? Then the order of a normal subgroup N not equal to E of G in H. N is contained in H. That's the catch here. Is 3 or 9. The answer is option 4. So that is the discussion of the solutions of the problems that have appeared in some of the competitive examinations. And these questions are, except this DL question that has come in degree lecturer exam, this question, all the questions are related to Sylow's theorems. I am sure that you have understood the concepts, theorems that I have explained and the problems and their solutions that I have shown you. I am sure that you have understood all these things and work out some more problems on these lines on Sylow's theorems, and it is a very important section. Thank you.